Hi everyone. So this is now week 6 to 8, and I'm going to run through these slides. I'm going to go a little quicker, not use R right now, principally because the commands are the same, except now with multiple regression, you have more independent or X variables. That's it. So we're going to focus on all of the topics, make multiple regression special from at a basic level, right? But otherwise, everything that we talked about in OLS or simple linear regression carries over. In particular, all of the stuff about the assumptions, right? Blue, the best linear unbiased estimator, bias, consistency, looking at the fundamental, most important assumption of exogeneity, wherein the mean of the population error conditional on the data x is 0, and all that stuff about regression diagnostics using plotting. All of that stuff carries over, so that's good. And we're just going to focus on the matters of interpretation for this particular set of slides. After this, we've got simulations. So now, next time, we will do a simulation of the population level issues, the endogeneity. What happens when the regressor is endogenous, right? It's no longer an exogenous regressor. So there is this relationship between the error term at the population level and X. What happens? What happens to OLS then? And then after that, we'll be talking about certain issues, about solutions, about things that you might encounter. Maybe even simulate again heteroscedasticity and just demonstrate how to solve that, the issue of how to solve for heteroscedastic error terms. And then finally, if we have time, we'll go into time series, and it's basically the same thing because the main problem with time series is serial correlation, which is a form of correlation amongst the errors. It's another form of heteroscedasticity, in other words. A very, very specific form of heteroscedasticity. That's only if you have time. But this is essentially the last big bulk of what you have to do to prepare yourself for the final quote-unquote basic project, which is to run a regression. Get data, run a regression, tell people about the structure of the data, what is an observation, what are you observing, right? The price, the weight, etc., whatever. And then plotting the variables, choose what the dependent variable and what's the independent variable, and then plot those, and then do the regression, and then interpret the coefficients, and then look at some tests on the residual. That's one of the things that we'll be talking about next week when we're doing the heteroscedasticity as well. When we're doing the simulations on heteroscedasticity, that there are more formal tests to test heteroscedasticity, which we will learn at that point. So you not only will you look at the residual plots, but you'll probably do a residuals based test, a formal statistical test. Okay, so there's lots of things to do. There's just not enough time, really. And we want to make sure that everyone knows the basics so that when you're moving on in your studies of econometrics, at least all of the stuff in R, you're able to learn and able to do. And that's a starting point for you to learn more techniques and to really connect the theory to the practice. Okay, so yun yung point. Okay, now let's go and talk about the slides here. Okay, so multiple regression is kind of like simple OLS, simple regression, except that instead of there's one independent variable, there are k potentially, or k is greater than 1, right? If it were equal to 1, it would be just the simple OLS, right? Now the idea is that each xk variable contributes to explaining the variation in y. One additional assumption here, now that you have multiple x's, is that the x's as a whole have variation and no two variables are not exactly correlated. If this is the case, the computer will ask you to exclude one of the variables. Right? It also makes sense logically. If two x variables are perfectly correlated, why are you adding both of them at the same time? So you might as well take one out. In terms of interpretation, each beta is interpreted as the effect on y for 1 unit of x, xk, right? Xk, I should say. Xk. Where is that? Correct. Note the units are important here. Some x's will have some units of quantity or money or even valueless units. So different x's will have different units. That's the point, right? Especially if they are continuous variables. So we discussed this in class before. Here's an example of multiple regression. So here you've got education. Now as a function of income and of young, right? The number of young people in each state, right? So again, this is the Enscombe data set. And all of this code you've done before, except now that you're adding this additional term or variable, right? So these words here are the column names, right? Or the names of each column in the data frame. Again, this is basic stuff. You should know it, okay? Practice doing the regression if you keep forgetting. And then you have this is the coefficient table, which you talk about. You have to be able to identify what the coefficients are and how to interpret them and to know which ones are significant and why. Why is income, the coefficient of income, significant, right? It's because the t-value is greater than the critical p-value and the p-value is very small. It's less than 0.05, which is also the critical p-value. All right. We also talked about this in class. Take note about the units of x. Okay, so you have to be very specific about the units of x. Okay, and the units of x will sort of help you interpret what the effect of a change in that x to education, which is beta. So beta is denominated in terms of the units of y. Yeah, that's it. Another example of multiple regression. So we talked about how transforming variables can help with heteroscedasticity. And I think we showed that with the Gapminder data, which is the GDP, income, poverty data set, the famous one. And we've got log education here is a function of log income and log young. And you've got the same coefficients. Again, interpret, figure out what this means. This is now an elasticity. A percent change in education as affected, a percentage in income now affects a percent change in education based on this coefficient, right? So a 1% increase in income will result in a 1.013137% increase in education spending per capita. So again, the interpretation is key here. Okay. Let's start. Now, linear hypothesis tests. Here, because there are multiple betas, now you can have multiple sort of tests on the values of different coefficients. The usual examples here are basically the equality of multiple coefficients, right? Such as this, are they the same or not? Right? Which we talked about in class already, I think, before. And it's quite simple. And let's conduct a test. Here is the model object which we created. This is the actual thing that we're interested in. Is the coefficient in income equal to young? Right. So this is what you mean by you say you do it symbolically. You write it symbolically, which is in the help file. So what we're doing really is we're behind the computer screen. You are estimating two models, model 1 and model 2. One is the restricted model where the coefficients are equal, restricted to be equal, and the other one where they are not. And it turns out that the p-value of the restriction is this. So you reject the restricted model because the p-value is less than 0.05. And because model 1, the hypothesis is that they're equal, that's called the null hypothesis. So if the p-value is small enough, then you reject the null hypothesis. Okay, so now interaction terms. So in multiple regression, we can now interact variables. So this is a simple model with an interaction term. You've got two continuous variables, x1 and then x2. And then now you're interacting them, x1 times x2, right? So this is now saying that the x1 and x2 sort of interact with each other to create changes in y. To do interactions, it's quite simple. All you need to do is, if it's something like this, like each one has a main effect, and then each one has an interaction, that all you need to do is to do log income star log young, and then that will give you that interaction. This, in the code or in the results, here are the main coefficients. That's the beta 1 and beta 2. And then here is the beta 1, 2, which is the interaction between the two. Okay, so the highlighted portion is the code needed to include an interaction. By using star, R will include the main effects and the interaction effects of the two variables that you have included. Now, if you have 3, then you just star all 3 of them, right? Then if you have 3, normally, technically you could have a 3-way interaction. That's totally fine. But then you'd have to really think about why you'd want to do that. So almost anything can be possible, except that you'd want to be able to like sort of justify doing that in terms of either the theory or like looking at the data. One way of justifying an interaction really is to show that the effect of income or young on education is sort of this nonlinear relationship that sort of depends on the value of the other, right? Because normally, if without this one, then it's quite clear. If x1 goes up by 1, then beta 1 is the effect. If x2 goes up by 1, then beta 2 is the effect. But what if you suspect and you look at the plots, and that's the reason why you plot, right? That if the effect on x1 on y seems to be this nonlinear thing, which may be due to the fact that x2 is sort of changing behind the scenes. So you can include an interaction to control for that. So the interpretation of the coefficients when an interaction term is involved. So now you take a derivative of y with respect to x1 in this case. And now instead of just b1, you have b1 plus the interaction term, where x1 goes away because you're taking the derivative with respect to x1. But now you have x2 remaining. So the effect of x1 depends on the value of x2. The total effect, so it becomes nonlinear, right? So instead of when x1 is going up, it really depends on what the x2 happens to be. Correct. On average, and again, regression is about coming up with an average effect. The average effect here is not just b1, but you can look at the average x2. So the average effect of x1 on y is beta 1 plus beta 1 2 times whatever the average x2 is. Okay. But overall, you would note that the effect of x1 on y depends on the value of x2 for sure. Now the total effect is from summing the main and the interaction effects. This is the main, b1, and b1 to x2, that's the interaction effect. Again, I talked about this already. How would you calculate? We would calculate the value of x2 to get that average effect of x1 on y, and then use that to get the total effect. So here, the average of x2 is 5.88. To get that, there are many ways. An obvious one would be to use the mean function, and then you calculate. Right? It's negative 3967 plus 0.045 times 0.588. Right, this is the average, and these are your coefficients, equals 1.02. Question, which is larger, the main effect or the interaction? Okay. So it should be obvious, right? If the main effect is negative, but when you add it, it becomes positive. Clearly, you know what's larger, right? It changes sign. Okay, so it's typically advised when dealing with interactions with different units. It would benefit from standardizing the variables first. So again, I go back to our discussion on standard normal, right? The idea of standardizing is you remove all of the units, and all of the units on the x-axis become standard deviations. Like 1 is 1 standard deviation away from the mean. 2 is 2 standard deviations. So those are the units. The units are now standard deviations away from the mean. So that's what standardizing does. So the z, you remove the average for x, and then you divide it by the standard deviation. Right? So if the value of this is exactly 1, okay, then that means that you are 1 standard deviation away from the mean. If it's equal to 0, then that means you are at the mean, because if the numerator is 0, that means it's equal to the mean. So therefore, you are at the mean. Now, the mean of the standardized of the z's is 0. So that helps with interpretation. So recall, in this situation, we would typically get the derivative. So we have this as the total effect. But you would replace z2 now with the mean. Now the mean of z2, as we discussed, is 0. So therefore, the interpretation of the coefficients is much simpler. b1 plus b12, and that's the total effect on y of a 1 unit change in z1, or a 1 standard deviation change in x, right? So you're not really thinking about the units of your x, whatever your x is. z1 might be different from z2, but because you standardize them, they are now both the same units. Z is now in standard deviations, and z2 is also in standard deviations, right? The number of standard deviations. Okay, so I hope it's clear that it's not only because the z goes away because z2 is 0, but it's that if you have multiple x's and you have these coordination or interaction between the two, then it would be good to have a standardized unit so that both of them would have the same standardized unit. So the units for b1 and b12 are essentially the same. Right, so you can add them up. Now beyond cross-section, so far we've been talking about cross-section, that's the basic model. Moving on, there's panel or multi-level data set. So a panel data contains observations of cross-sectional units over time. So in our rice example, you've got rice varieties at the stall level over different months or weeks. Right? Or a cross-section can have a richer data structure. So it doesn't have to be over time. It could have multiple subsets. So similar to, again, the rice data, you've got cities, and then you've got, that's probably not a good example, actually. So yeah, let's stick with this. So on a cross-section, you can have a richer structure. So you have a province, an overall province, and then you have cities in the province. And then a province as being in a group, maybe a region. Or it can be both, a panel with the richer data structure, with part of the discrete groupings this time. Typically, the data groupings and structure is represented by a discrete variable. So in the rice data set, it would include the city and the variety of rice. Yeah. Okay, so now we'll focus on regressions with discrete variables. So that's the interesting part. Discrete variables are essentially categorical variables, right, or factor variables in R. And what that will do is sort of allow you to calculate the averages for each group, the average y for each group, each discrete variable, each value of the discrete variable. So here you can make comparisons over groups, right, which is the structure of the data set, the different groups. So using the rice data set, we can ask questions like, what is the difference in the average price of regular milled rice between 2018 and 2017? This will lead you to an estimate of the difference in the hypothesis test. The natural one would be, are they equal to each other? So is the price of 2018 equal to that of 2017? Okay, so here's our rice data set. This comes from the file linearreg2 discrete and continuous. The rice data set there. What's cool about it is it has a bunch of other variables, retail, farm gate, and production. And you've got provinces here as the location and years. I think there are 2 years. So our regression here is retail price as a function of year and location and farm gate. So this is multiple regression. Year and location, those are discrete variables, and farm gate is a continuous variable. So you do summary reg 1 as usual. Output is long, which is usual if you have a lot of different groups. And this is like just a snippet of the output, this one, right? And again, I invite you to interpret, right? But what's most important for our case here is like the interpretation of the discrete variables, okay? Right. We already know how to interpret the continuous variable here, and this is the continuous variable. So the first thing to observe is the intercept when it comes to having multiple discrete variables. The intercept is the value of the dependent variable retail price for the base case. So what is the base case? It's the discrete case that is left out of the listings here in the table. For the year, it's 2017. So the intercept essentially contains the year information on the year 2017. And for location, it's ABRA, which is the first letter of the alphabet. Again, it's alphabetical. That's the default position. The first province is alphabetically determined. Second, the year 2018 variable is 1.27. So this is the price difference between 2017, the base case, and 2018. Control for the other variables, which are locations and farm gate prices. So the price change is the average of all provinces in the specification. And controlling for the average farm gate. We can have interactions among discrete variables also. In this case, we can have an interaction between year and location. Now, what is the comparison between 2017 and 2018 with an interaction on a location? Okay. Another way of saying it is the price change between years depends on the province. So the code can be as follows. So now we use the star to have the main effects for year and location and their interactions as well. So you do summary. What will come out? It's long, right? It's long. But what you wanted to point out here is that at the end of it, you'd have this, which is the interaction between year, which is 2018, and the places, all of the provinces. So in particular, for these two ones that I'm showing, they are not significant. Okay. However, that doesn't necessarily mean we know what the full effect is. For, say, Agusan del Norte, that you should just ignore it. Okay. What this just means is that statistically, there is no difference between Abra and Agusan del Norte, and the difference between 20 in the comparison of 2017 and 2018. Okay. However, the total effect for Agusan del Norte's price, if you're interested in Agusan del Norte's price, is, and based on the formula we had, it would be negative 0.16.21, which is year. That's the main effect. Remember, we're comparing 2017 2018. But we're wondering if on the location, if it matters, right? If it matters that it's Agusan del Norte. And the effect of the interaction is 0.08. Okay. And the full specific effect for Agusan del Norte is 0.08 because it's 0.16 plus 0.08. So that is the computed full effect for Agusan del Norte. Okay. Of course, because the interaction itself is not significant, then you could say, statistically speaking, that there is no difference between the price difference over 2017-2018 of Agusan del Norte and Abra, right? Because those are the comparisons. That's what we're comparing here, Agusan del Norte and Abra, right? Whether this is zero or not. It's relative to Abra, which is the base case. Interactions with discrete variables. The question is, was there statistically significant increase in the price in Agusan del Norte? The question is, negative 0.08 statistically is different from zero. So we already know the answer here. But you can also do it using the linear hypothesis test, which you've done here. The hypothesis is this plus this okay, is 0, right? Oh, well, actually, what this is saying actually is that was there a statistically significant increase in price in Agusan del Norte, right? And the question is absolutely going to be, well, let's find out, right? Because we need to use the linear hypothesis test. And what we're doing is we're saying that the sum of this plus this is equal to 0, right? And recall that the sum there is negative 0.08. So the question is the sum statistically significant from 0? And this p-value is larger than 0.05. So we accept the null hypothesis here. We accept the null hypothesis here. That for Agusan del Norte specifically, that there is no change in the price of rice. Okay, because we cannot reject the hypothesis here that the sum is equal to 0. Similarly, there can be interactions between continuous and discrete variables, right? So we have a continuous variable in the model, which is farm gate, and then we can interact that with any discrete variable, which here is either the year or the location. So again, the effect of the dependent variable on the continuous by the continuous regressor depends on the value of the discrete variable. The marginal effect of the continuous variable depends on the value of the discrete variable. Again, you can do the calculation that we did before. The calculation meaning the derivative, the first derivative of y with respect to the dependent, to the continuous regressor. Okay, so consider the regression. I left that blank because it should be clear here what the model is. Okay, so by looking at the coefficients table, then you should know that our dependent variable, well, still is retail. We are doing it as a function of year, farm gate, location, and an interaction between farm gate and location. Okay, so you should be able to write what the model is. Okay, similar to this, right? Instead of this, it's gonna be different in order to come up with this. So this is something that you should try writing it right now, right? And in class, I'll probably do it together. Okay, so the effect of farm gate on retail prices now depends on location. For Agusan del Norte, it's negative 0.03 minus 0.49 because of this, which is minus 0.52. For Antique, it's negative 0.03 plus 0.95, which is 0.92. So in one place it's negative and in one place it's positive. For which place does Farmgate have a statistically significant effect on retail price? So again, you are looking at the coefficients here. Okay. Actually, I'm not sure if this is homework. I'm going to check. I'm not sure if this is homework. I'm going to check tonight if this is still the homework. But the idea here is you can look at the interaction terms here, right? Because these now would tell you which places where there is a statistically significant effect on retail price by location. So that matters. So you'd have to then run the linear restriction to know if in a particular place there is this particular well, these ones are about a comparison between Agusan del Norte and Abra. So the question, for example, here is that between Agusan and Abra, there is no statistically significant difference in the effect of Farmgate. If you were to say, well, yeah, so that's the interpretation of the coefficients here, the interactions here. is there a statistically different relationship between farm gate and the location between Agusan and the base case, which is Abra? And the answer is negative 0.49, but it's statistically insignificant. So between Agusan and the Agusan and Abra, there is no um, statistically different difference between Agusan del Norte and Abra. Okay, and that ends our slides. Please go back and make sure you try to run all of this code in R, and then make sure you understand the interpretation of the tables and how to interpret the interaction terms for continuous and discrete variables. Having said that, bye bye. Thank you.